In the previous chapter about acid-base equilibrium, we learned about the Bronsted acid-base theory. And we are actually going to finish up this chapter, this section, with another theory called the Lewis acid-base theory. So the Lewis acid-base theory focuses on electrons, which makes sense. Remember, Lewis structures have to do with us counting up valence electrons and then beginning to build the molecule and bonds based off of that. So of course, Lewis acids and bases have to do with electrons. So a lone pair is what allows a bond to form, or a bond can turn into a lone pair in Lewis acid-base theory. So in this theory, we do not require protons or H atoms as we do in the Bronsted theory. So in the Bronsted theory, we say that acids are proton donors and bases are proton acceptors, right? But in this theory, we do not require those. So a Lewis base is an electron donor. It's electron rich in comparison to a Lewis acid, which is electron deficient, doesn't have any electrons, so it accepts them. So there are two words that we use to describe these. So something that is electron rich is called a nucleophile. And the reason for this is because it wants a nucleus, so it'll attack a nucleus in a sense to give those electrons to that nucleus, while an acid, which does not have electrons, is called an electrophile because it wants electrons. So if you don't know what this suffix means, phile means like loving, so a nucleophile means that it wants or it loves nuclei. And then for electrophile, it means that it wants electrons, right? Or it needs electrons. So a Lewis base has electrons that it can give away or share with another atom. And this also means it has to have a lone pair that it can donate. So usually what make better Lewis bases are anions. And the reason for this is because they usually have an extra electron, right? So for any anion, the definition of an anion is that you gain electrons. So they obviously have extra electrons. So this makes them better Lewis bases in comparison to their neutral counterparts for this case. The more electronegative an atom is, the less willing it is to be a Lewis base. So you can think of it again, electronegativity is like when an atom hogs electrons towards itself. So for example, fluorine is very electronegative. It will want to hog electrons towards itself very much in comparison to every other element. It's the most electronegative atom on the periodic table. So because of this, you can think of it like it being selfish. So very electronegative atoms, they don't want to give up those electrons, that lone pair, in order to be Lewis base. So oxygen is more electronegative in comparison to sulfur. So sulfur is more willing to be a Lewis base in comparison to oxygen because of that. In contrast, Lewis acids are electron deficient, meaning that they usually will not have an octet, or they will be attached to an electronegative atom that causes them to be electron deficient. So remember, electronegative atoms are selfish. They hog electrons toward themselves. And whenever they do that, they also kind of strip away electrons from whatever it's bonded to. So they're being selfish, basically. So in order for something to be an acid, it either has to be one of these two cases, either electron deficient or not having an octet. So Lewis acids must have an empty orbital where they can accept that pair. So for example, H plus has no electrons. So what it has is just an empty 1s orbital. So this is electron deficient, so that means it can act as an acid. Now boron in BF3 has an empty 2p orbital and an incomplete octet. So if we were to draw the Lewis structure for BF3, you would see that it's like this. And obviously there's lone pairs on all the fluorine. So if you actually counted up all the total valence electrons, this is the overall structure we would get. And what we see here is that the boron only has 6 electrons around it, and it's actually only using a 2s orbital and 2p orbitals. So there's 2s, and then there's 3 separate 2p orbitals, right? So in this case, this boron is using this one, and this one, right? I'm just going to color them in. And it has an empty 2p orbital. And overall, this causes this incomplete octet. And because of this, it is able and willing to accept an electron pair and act as a Lewis acid. So many small, highly charged metal cations have a similar situation where they have empty orbitals. They can use these to accept electrons. And then atoms that are attached to highly electronegative atoms, like I talked about earlier, these can act as acids because they're basically electron deficient, because the electronegative atom is kind of hoarding away the electrons. So let's look at some reactions. We know that the base donates a pair of electrons to the acid. That's the main idea of Lewis acids and bases. But what actually forms is something called a coordinate covalent bond, or a dative bond. This is a bond that happens whenever one of the atoms completely gives up 2 of its electrons to form the bond. So usually a covalent bond is that they're sharing, right? One atom is giving one of the electrons, the other atom is contributing the other electron. They share the 2 to form a bond. But in a coordinate covalent bond, one of the elements, or one of the atoms, is completely giving up those 2 to form that bond. So here we have water and we have a proton, right, with no electrons, meaning it has none at all, actually. So it has none to give. So whenever it forms this covalent bond right here, water, or the oxygen in the water, is the one that's completely giving up that pair to form that bond between these 2. So this is a coordinate covalent bond. And the same thing here, whenever we have ammonia and it turning into ammonium, that H has no electrons. So the N right here is the one that's completely sharing its electrons to form that bond. Overall, the product that you get from a Lewis acid base reaction is called an adduct. So here we have a Lewis acid and a base, right? The base is the one that's going to be giving up the pair of electrons, and the acid is accepting. This right here is an adduct, or your product. Here we have some more examples. We have our Lewis base that has obviously a lone pair, and then it reacts with our Lewis acid, which is a proton that has no electrons, so it's electron deficient, and then it reacts with it and you get your adduct right here. But you also get the anion that was originally on the Lewis acid in solution, so that's why that's there. And then here we have another Lewis base giving up its lone pair. It's attacking that nucleus of that boron. This boron is electron deficient, so that's why it's a Lewis acid. It doesn't have 8 electrons around it, only has 6. And remember, we also talked about nucleophile versus electrophile. So a Lewis base is a nucleophile. If you learn these terms right now, it'll be easier if you take organic chemistry, because these terms do come up again. While the Lewis acid is an electrophile, like it's like, give me those electrons. That's why the electrons are being given to it. And the Lewis base is like, yes, I need a nucleus to give these electrons to. And then you get your adduct as your product. And this right here is a coordinate covalent bond. So transition metals actually tend to be good Lewis acids. And again, this is because they have empty orbitals and they can accept electrons in those orbitals. So they will often bond to one or more H2O molecules to form a hydrated ion. H2O is the one that's acting as a Lewis base. If you remember the structure of H2O, it has some lone pairs on that oxygen, so that's why it can act as a base. So it'll donate electron pairs to form those coordinate covalent bonds. So here we have a transition metal silver reacting with water, and you end up getting the adduct here as your product. So ions that form by combining a cation with several anions or neutral molecules are called complex ions. So if you notice here, it has an ionic charge overall, a plus charge, a positive charge. So this is an example of one of these. And overall, the attached ions or molecules, the molecules can be neutral, as water is. These are called ligands. So the water is a ligand, and the overall product you get is a complex ion. So as the other topics we visited that are in equilibrium, we also can have complex ion equilibrium. So if a ligand is added to a solution that forms a stronger bond than the current ligand, it will replace the current ligand. So remember, these solutions are very dynamic. They're not just static, forming a product that can't be like reversed or anything. So because of this, you can have competition if you add a different ligand. So here we have ammonia as the ligand in this case. And what it's doing is replacing the water that was originally in the complex ion. So here you get a different complex ion, right, as the product. And you kind of displace water. And we have finally another K value. So the reaction between an ion and ligands to form the complex ion is called a complex ion formation reaction. And what we can express for this complex ion formation reaction is a formation constant, so a Kf. So it's not the same Kf about like the constant for freezing back in like chapter 10. This is capital Kf, okay? So it has to do with equilibrium. But here we have this reaction of our transition metal with a ligand right here and forming a complex ion. And if we look at the overall constant, the formation constant or equilibrium constant, we have our product over our reactants. So it's the same setup. There's nothing new with that. Here are some formation constants for certain complex ions in water at 25 degrees C. So some of these are very favorable. As you can see, they have very high Kf values, meaning that they like forming the products. 10 to the 30, that's insane. So some of these are very like favorable to form. So let's look visually at how these complex ions form. So first we would have NH3 in solution, right, aqueous in water. So here we have that ammonia solution up here. And then down here in this beaker, we have solid sodium chloride, right? Solid sodium chloride is sparingly soluble, so most of it will be solid, and then there will be some dissolved in solution. But we have them separate, and then you add the ammonia aqueous solution into the silver chloride, and what you see is that the silver starts reacting with the ammonia to form a complex ion, and then you have chloride in solution, and then this should be a negative sign. And the way I think of it is that the fact that this complex ion is forming and kind of leaching away the silver in solution, it kind of causes a shift. And the shift it causes is for the AgCl, whatever is in solution, the solid, to end up forming more silver in solution, right? Because whatever was in solution formed this complex ion. So it shifts the equilibrium to make the silver chloride more soluble. And I think you can see hopefully on this picture how there's less of that powder, right, compared to there. And it's because it's forming this, so then the equilibrium's like, oh no, there's no silver. So whatever is here as a solid, it starts being more soluble because of that. So it's all about equilibrium. Remember, it's very dynamic. If there's a change, it'll adjust to fix that change. So here we have the same example, except written out. Here we have solid silver chloride, and it has a certain KSP value to it. And then here we have the complex ion formation. So we have the Kf value. As you form more of your complex ion, so if you keep adding NH3 to a solution in equilibrium with AgCl solid, this will increase the solubility of Ag. So you'll, again, this, because you're adding that in there and you're forming that very favorable product, that complex ion, then you're kind of leaching out whatever Ag is in solution. So this causes this to shift more that way. So you're probably looking at this ice table right now, and you're probably like, oh my God, when are these going to end? These are the last ones in this chapter. This is the last one in this chapter that I care about you being able to solve, okay? There are more in 15.3. We're on section 15.2 right now, but on 15.3, I kind of kept it simple, and we're just going to look at the concept, not calculate anything, because there's so much already that you have to do, and it's just insane. So this is the last one for this chapter. So in this one, we are looking at the dissociation of a complex ion. So we're going to calculate the concentration of silver ion in a solution that is initially 0.10 molar with respect to Ag NH3 complex ion. So if we look at this little table that conveniently is already here, but if we had to develop it like on our own, first we would look at the equation, right? The equation for this complex ion formation. And then we know that what you have in solution is silver, and then you're adding in ammonia. So think of that earlier picture with the little droplets of ammonia being added in, and then, you know, forming that complex ion that was soluble. So that's what's going on here. So initially you don't have any silver and you don't have any ammonia, because we know that what we're given is the concentration of the complex ion. So we want to find out how much of the silver ion we had for a solution that originally was this concentration of this complex ion. So we're kind of going backwards, right? So we're going this way. So we originally had 0.1 molar of this complex ion. Because we're going right to the left and trying to figure out the silver ion, we have a negative sign in front of this change. For this, we have positive and positive. And as far as the numbers, it has to do with the stoichiometry. So here it's 2x, here it's just 1x. And then here we have our equilibrium concentration changes. So what we should do now at this point is figure out what our Kf expression is. So remember, your Kf is your formation constant. So it's going to be your product, your complex ion, over your reactants, which is Ag plus, and then NH3 raised to 2 because of that coefficient. And so the Kf value for this particular reaction is actually 1.7 times 10 to the 7th. This can be found on that table we were talking about, and also usually I would just give it, I just forgot to include it in here, but usually I would say, you know, your Kf is equal to blah blah blah. So that's what our Kf is equal to, and then we can plug everything else in. So for AgNO3 we have, sorry, AgNH3, our complex ion, we have 0.10 minus x over our x, right, for our silver ion, and then 2x squared for our ammonia ligands. So we can go ahead and do that little trick again where we make the assumption. So the assumption we're making is that the change right here, I'm going to highlight it in a different color, the change in concentration is very small. And we make this assumption because we know that the equilibrium constant is very big in this case. So when something is very small or very big for these K values, we can assume that the change will be very small. So because we know that it's very favorable, right, this is a huge number, it's very favorable for this complex to form, then we can say that whatever change happens will be tiny. So we can go ahead and just disregard that. What we end up with is 1.7 times 10 to the 7th, 0.1 x 2x squared. We can further simplify this to be 1.7 times 10 to the 7th equals 0.1, and then we would square this, so you get 4x squared. Further, you can just multiply that x by it, so we end up getting 1.7 times 10 to the 7th equals, I'm just doing algebra here, 4x cubed. So this is about as simple as we can get before we need to start solving, right? So I would solve for this, and through a little algebra trick. So we could go through like multiplying each side and dividing in order to isolate this x cubed that is in the denominator. But something faster that you can do is switch sides. So switch places. So we are going to switch this with this. So if we were to do the algebra, that's what you would end up getting. Like it flips places. So instead what we get is 4 times 1.7 times 10 to the 7th. It's a 0. That's a 7. Okay, so now what we can do is go ahead and solve that out and then take the cube root. So if I simplify this, I get x cubed equals 1.5 times 10 to the negative 9th. Now your next step is to cube root. So instead of just square root, which is root of 2, we're going to do a cube root. So this cancels out that cube right there. And what we should get from there, so I'm going up this time, is x equals 1.1 times 10 to the negative 3. If you need help typing in that cube root, just let me know. Your calculator should have a button for that, like where you can enter the specific root that you're trying to do. But if you need help, just let me know. So overall, we solved for x and we found that it's 1.1 times 10 to the negative 3. So this is our amount of silver. So remember, the amount of silver at equilibrium that we figured out based off the ice table was x. So your silver concentration is 1.1 times 10 to the negative 3 molar, and that's your answer. We have finally reached the last section of this chapter. It's section 15.3, coupled equilibria. And coupled equilibria, that's something actually came up in, I believe, the fundamental equilibrium constants in chapter 13. And this is whenever we have a stepwise process and each of these steps has its own equilibrium constant, and then we can combine steps to get an overall like unknown equilibrium constant. So sometimes more than one equilibrium is needed to describe a process. So for example, dissolving an ionic solid with a strong acid, you're first going to have to do one step and then it's followed by a separate step. Dissolving a sparingly soluble solid by complex ion formation. So this example we just did, where we had first the AgCl in solution at equilibrium and then you added in a ligand to form that complex ion. And then another example is the carbonate chemistry in our oceans, and I'm going to talk about that for this particular section. So just know the overall concept that we can have several steps to describe a process, and you know they each have their own equilibrium constants associated with them. So to understand the idea of coupled equilibria, we are going to look at how ocean acidification is affecting coral reefs. So we have an increasing amount of carbon dioxide in our atmosphere, right? This carbon dioxide doesn't just stay in the atmosphere. It actually dissolves into water. So you'll have carbon dioxide gas in the atmosphere, And if you increase this amount, it's going to shift to adjust that, right? That equilibrium. And you're going to end up having more in solution in water. That's why it says aqueous. So first you have that being dissolved. Now, once you have that CO2 dissolved into water, it doesn't just hang around. So like you always have subsequent chemical reactions. So it doesn't just hang around. It actually reacts with water. So it'll react with water molecules and you end up getting carbonic acid, which is H2CO3 aqueous. This carbonic acid will react with water again and you end up getting hydronium in solution. So now you have an ion and hydronium. Increase in hydronium means an increase in acidity, right? Which means a drop in pH. So overall, can you see, hopefully you can see how we have an increase in the acidity of the ocean because of that original additional CO2 being dissolved into water. So here we have more acid, right? This will again ionize with water again. So it has two processes where it can increase the amount of hydronium. So if you remember from the acid chapter, where some acids are diprotic, so meaning they can give off two of their protons. So you can see how it has two protons, so that's why there's two steps for this. But overall, just understand that there's an increase in hydronium, which means you have more acidic environment. Now, this increase in hydronium, what is it doing to the calcium carbonate that helps form the reefs? It is actually, again, reacting with this calcium carbonate. So if it's reacting with calcium carbonate, you end up getting calcium in solution. You form this bicarbonate ion and also some extra water molecules. So what you have occurring in terms of the reefs is this reaction right here, and also the previous reaction that has to do with just calcium carbonate going into solution as calcium ion and carbonate ion. So you have your KSP value and your Ka2. So this coupled equilibria, you would divide both of these and you end up getting your new K value. So notice that this K value, this equilibrium constant, is much greater than the KSP value. The KSP value was just 8 points, so I'm just going to write it off to the side. It's from the previous slide. 8.7 times 10 to the negative 9th. It's a lot greater. Times 10 to the negative 9th is a tiny number compared to 180. So because of this, we have a increasing solubility of calcium in acidic solutions. So overall, as carbon dioxide levels in the atmosphere increase, they also increase the acidity, and then you also cause more dissolution of your original calcium carbonate. So in normal environment, at a more ideal environment, the calcium is dissolved to a certain extent, right? The calcium from the calcium carbonate of the reefs. But with this increase in acid, this causes the calcium to become more soluble, more prone to dissolution, and because of this, like, everything just gets messed up and overall the reefs are less healthy. So this is how this increase in acidity in the ocean is affecting coral reefs. And again, the main idea I want to illustrate here is how these equilibria are connected, so they're overall coupled. So for this section, don't worry about calculating anything. I just want you to understand how, like, overall chemical reactions can be because of coupled separate steps, and you can look at and calculate a unknown equilibrium through these steps.